Hello, good day. We are Group 3 of CPE108 Microprocessors Laboratory of Section E02 under Professor Cyrel Manlises. We are going to present about our design of experiment, which is all about the BCD to Gray-code converter. This is a cell phone Cipat speaking, and I'm going to present by starting with the objectives. The objectives of this experiment are the following. We need to apply what we have learned on the previous experiments within the term. We need to also be familiar and understand the principles behind the BCD and Gray system, which includes the conversion itself. We need to derive and formulate the necessary Boolean expression to run the program. And lastly, we have to use the CPE108 simulator to convert BCD inputs to Gray code outputs. Here, we are going to utilize the features of the simulator for the inputs, and the LED will be used for the output. First things first, we have to compare the BCD and Gray code system in order for us to introduce a short graph about each number system. BCD, or binary coded decimal, is a class of binary encodings of decimal numbers where each digit is assigned by a fixed number of bits, usually 4 or 8 bits. The BCD system takes advantage of the fact that any one decimal digit can be represented by an assigned 4-bit parallel. On the other hand, the Gray code system is an ordering of the binary numeral system such that two successive values differ only in 1 bit. The table on the right shows the relationship between the decimal number, the BCD equivalent, and the Gray code equivalent. Note that the BCD equivalent on the second column and the Gray code column on the third column differs only in 1 bit. In this slide, we are going to give an example on how to convert BCD to Gray code manually. To convert BCD to Gray code, each bit of the binary will be compared to the next bit using an XOR operation from left to right. From the truth table of the XOR operation, it can be observed that if the two inputs are different, its output will be equivalent to 1, else 0. The truth table can be shown below. From the truth table of the XOR operation, we can observe that if the inputs are the same, its output will be 0. And if the two inputs are different, its output will be equal to 1. In the next slide, I will show you an example of conversion from BCD to Gray code equivalent. Here's an example of a manual conversion. We have the given convert 001 BCD to its equivalent Gray code. To convert a given BCD to its equivalent Gray code, each digit from the given BCD must be compared to the next digit to its right. To compare, we use the XOR operation. Taking the first two digits from the leftmost side of the given 4-bit number, we apply an XOR operation to 0, and the next digit to its right, which happens to be 0. 0 XOR to 0 is 0. Taking the result from the operation above, we proceed to the next digit, which happens to be also 0. 0 XOR to 0 will be equal to 0. This time, the next digit of the result above will be 1. Applying the XOR operation, 0 XOR to 1 is equal to 1. Lastly, we apply another XOR operation to the result from the last operation, which is 1, and to the remaining digit of the given, which happens to be also 1. We have 1 XOR to 1 is equal to 0. Finally, we now have the Gray code equivalent of the 001 BCD by simply applying successive XOR operations to each digit, starting from the leftmost bit of the given BCD. We have 001 BCD is equal to 0010 Gray code. On this slide, we have the BCD to Gray code truth table. Note that for inputs 10 to 15 and their outputs are marked X, which means that the outputs falls under don't care conditions. Its BCD systems only utilizes the digits 0 to 9. Verifying the result from the previous example, we can use the truth table. The gray code equivalent of 0011 BCD is equal to 0010. We can now proceed to the Boolean expressions. From the outputs of the program, each output WXYZ has a condition where their value will be equal to 1. Applying the Carnot map from the logic circuits lecture, we can derive the Boolean expressions for each output. We have W equals A, X is equal to A or with B, Y is equal to complement of B, and then with C, or with the B, and then with the complement of C. And lastly, we have Z is equal to the complement of C and then with D, or with the complement of D and then with C. Derived Boolean expressions from the last slide, we can now have its logic circuit. Note that the switches on the left are labeled as A, B, C, and D from top to bottom, and also the outputs LED on the right are labeled W, X, Y, and Z from top to bottom. We now proceed to the EDSIM51 simulation. The program created will convert BCD inputs to gray code outputs in terms of switches and LEDs. The program will display the input values first in LEDs. After a time delay, it will not immediately display the converted values from BCD to gray code. Here, core rightmost switches will be used as inputs to designate 4-bit entries to the program, which can be read from left to right as 8, 4, 2, 1. As for the output, 4 LEDs will be assigned to display the resultant of the converted inputs with the same convention as the input to be read from left to right, with each bit to be 8, 4, 2, and 1. This slide shows the program flowchart, from the start of the program up to the end of the program. From the start, accumulator content is declared before calling time delay. We have the decision to make if there is an input. If yes, we move the P2 switch content to the accumulator. Then complement the accumulator content. We then move the accumulator content to the P1, which are the LEDs. We need to load the accumulator content to register B, clear carry flag, and to perform XOR operations on the accumulator and register B. From the result of the XOR operation, we can now display the result of the XOR operation in terms of LEDs. That's all.
Good day. I am Richard Vincent D. Chua, the groupmate of Josef Cipat, and I will show you the continuation of the design of the experiment. This part shows the procedure on how to start the program and how to use the program using the EDSIM51 simulator. First, launch the EDSIM51 simulator, click New, and encode the following address starting at address 0000 hexa. To save the program, click Save, assemble the program, click Update Frequency, and choose whatever you want. Run the program, and upon running the program, press your desired BCD equivalent values on the switch. For us, we will try all possible binary inputs to show if the program is really working. And observe the output of the program. We'll go to the simulator, zoom in, and I will give you a truth table for BCD to gray converter, show in the screen, and we will try to input all of it. Click assemble, run, and now the program is running. we will input 0, 0, 0, 0 by not pressing any button. By not pressing any button, we will have a binary input of 0, 0, 0, 0 and a gray output of 0, 0, 0, 0. Upon pressing switch 0, this will give us a binary input of 0, 0, 0, 1 and will give us a gray output of 0, 0, 0, 1. By pressing switch 1 only, this will give us a binary input of 0, 0, 1, 0 and a gray output of 0, 0, 1, 1. By pressing switch 1 and switch 0, this will give us a binary input of 0, 0, 1, 1 and a gray output of 0, 0, 1, 0. By pressing switch 2 only, this will give us a binary input of 0, 1, 0, 0 and a gray output of 0, 1, 1, 0. By pressing switch 0 and switch 2, this will give us a binary input of 0, 1, 0, 1 and will give us a gray input of 0, 1, 1, 1. By pressing switch 2 and 1 only, this will give us a binary input of 0, 1, 1, 0 and a gray output of 0, 1, 0, 1. By pressing switch 2, switch 1 and switch 0, this will give us a binary input of 0, 1, 1, 1 and a gray output of 0, 1, 0, 0. By pressing switch 3 only, this will give us a binary input of 1, 0, 0, 0 and an output of 1, 1, 0, 0. And lastly, as the truth table said, by pressing switch 3 and switch 0, this will give us a binary input of 1, 0, 0, 1 and an output of 1, 1, 0, 1. I did not input inputs for later than 1, 0, 0, 1 because it will output a don't care condition. Upon checking the truth table, all the gray conversion of each binary input is correct. Therefore, this program is working and is reliable. Discussion. The experiment is about the conversion of BCD to gray code system. The BCD system accepts equivalent binary digits of decimals 0 to 9. From that, the remaining binary equivalents of 10 to 15 will fall under don't care conditions. As for the background of gray code system, it is said that it is an ordering of binary number system wherein two successive values differ in only one bit. This is done by performing an XOR operation when comparing each bit of the number from a left to right manner. The experiment was simple enough if it were not for the formulation of the codes. As said above, the BCD to gray conversion can be done manually by performing successive XOR operations on each bit. In this experiment, we were able to verify the reliability and integrity of the program since all the possible input entries and their corresponding output values were correct. Using the truth table above, we were able to check all inputs and their corresponding outputs respectively. For the conclusion, after thoroughly studying the concepts, designing the program, and performing the experiment, we were able to satisfy and meet the objectives we have set. We were able to apply what we have learned in the whole quarter, where we have applied the instructions and algorithms of the EdSim 51 simulator, specifically time delay, switching, and integrating the desired output to the LEDs. From studying the background of the conversion, creating the truth table, derivation of the Boolean expression, designing the logic circuit, creating the flowchart, formulating the accurate code of the program, and testing, we have successfully designed and implemented a BCD to Gray code converter on the EdSim 51 simulator. Thanks for listening. This is our design of experiment. Goodbye.